What's that?
You use the scanner, you're like 2 hours.
You know what? It's one of those things where I didn't do it intentionally, but whoever used the machine before me had the settings so that it would add one page to another, and so now I've got a single. I've got to figure out how to make the scanner do that itself.
That's actually pretty cool. That's easier for you to just scroll down.
Yeah. I just didn't know how to do that previously, and I've been so strapped for time I haven't had the chance to figure it out. Okay, so we're going to have a really brief lecture today. We're going to have a really brief lecture today, just kind of reminding ourselves about a few things that we learned last week regarding entropy, and then we're going to open up the rest of the day to actually just trying to solve problems, because I feel like the majority of learning gets done solving the problems, and so I'll be quick, just do a really quick review, add a couple things onto it, and then we're going to open up homework number 3, and I think I'm going to pull out a problem from one of the exams and show that to you, and we'll do some group work together. So last week we looked at the Carnot cycle, and we showed that that people who were doing calculations found out that as you trace that Carnot cycle in a full loop, that it ends up that that ratio of Q over T traced along the cycle, so the heat leaving or entering at any stage in the cycle divided by the temperature at which that heat is transferred, the sum of that around the cycle ends up being 0. And we know that state functions have the property that the integral around a closed path for a state function is 0. So that pointed out to these guys that they were dealing with a new form, a new kind of a state function. We end up writing the state function, the differential of the state function is ds is equal to dq reversible over t. The Carnot cycle, all the steps were reversible, and so that state function s is it's ds is or the integral of s is 0, but only if you trace it along a reversible path. So our definition of entropy includes that dq reversible over t, and then we've got the statistical definition of entropy, which is that s is equal to kV, Boltzmann constant, times the natural log of w, where w is, it can be called the weight or the ways, but what it refers to is the number of different arrangements of equivalent energy that are available to a system. So you take a system and you stick a bunch of energy into it, and it's forced to kind of distribute the energy amongst the particles that it has. And systems that have larger numbers of different ways to distribute that energy amongst their particles, those systems have the larger entropy. And so you'll notice that that goes as the natural logarithm of W. As the number of ways to distribute the energy amongst your system increases, then S increases. We looked at a couple of processes that occurred in closed systems, or isolated systems. Isolated systems are systems that have no exchange of energy or anything else with the surroundings. And so we showed that the expansion of an ideal gas to a larger volume is a spontaneous process. If there's no external pressure on it, so that's called free expansion. And we calculated the entropy for that free expansion. We also showed that a composite system composed of 2 blocks of metal that are touching each other will spontaneously distribute that energy until the temperature of the 2 blocks is identical. And we ran a calculation to figure out what delta S was for that. The take-home message of those 2 experiments, or those 2 calculations, was that an isolated system undergoing a spontaneous process, any spontaneous process that occurs in an isolated system, results in an increase in that state function entropy, right? So delta S will be positive for a spontaneous process that occurs in an isolated system. What we're going to talk about on Thursday a little bit more, we're not going to get into it so much today, but we'll talk about on Thursday, is that the standard that delta S has to be positive for a spontaneous process is true not only for an isolated system, but also for a system that is in contact with the surroundings. But in that case, you are not free only, or you're not allowed to simply calculate the delta S of the system. You have to include the delta S of the surroundings as well. So isolated systems like that free expansion of the gas and the two blocks equilibrating, then the total delta S of the system has to be positive. For a system in contact with the surroundings, on the other hand, the total delta S of the universe has to be positive, which means that the system might be decreasing in entropy, but as long as the surroundings is increasing in entropy more than the system, then the process will occur spontaneously, and vice versa. So as long as there's a net increase in entropy, you're going to have a spontaneous process. Okay? So, just a reminder, when we calculated that volume change, you can look back at the notes from last week, but we showed that while there is the statistical method for calculating delta S, we can also calculate delta S for a volume change by finding a reversible path between the initial states and the final states, and that's something I want you to remember. The statement that you need to find a reversible path. Whenever you're doing entropy calculations, you'll have an initial state and a final state of the system. And regardless of whether or not the actual process occurs reversibly or irreversibly, if you're calculating entropy, you have to find a reversible path that links you between the two states. And if you calculate dq reversible over t along that path, you'll get the entropy change for the change in state. And so when we were doing that volume one, we said ds is dq reversible over t, and we were forced to try to find a reversible process that would lead us from one volume to the other while not changing the temperature. Remember, it was a free expansion, it was isothermal, and ideal gases don't have intermolecular forces, and so there's no temperature change associated with expansion for an ideal gas. So we needed to find an isothermal reversible path that would lead us from our initial volume to our final volume. And we noted that isothermal reversible expansion is just such a path. And so we calculated dq for that isothermal reversible expansion. And remember, for isothermal, because delta U is 0, then dq is equal to negative dw. And dw is p external dv. And for a reversible process, p external is equal to p internal. Sorry if this is going kind of fast. But we put in nRT over v for the p internal. And then we've got this other factor of t here because of the definition of entropy. And so we end up integrating nr over v dv after the t's cancel, and we get nr line v final over v initial. And that's the simple statement for the change in entropy when you have a change in volume. Anytime you have a change in volume, you're going to have a change in entropy. We'll talk a little bit more about what this means quantum mechanically, but you can think of it very simply as more space being available to the system. There's a larger number of ways to arrange the matter in that space, right? So as the volume of a system grows, the entropy of that system grows because there's a larger variety of ways that you can distribute the matter throughout that system. Yeah? So kind of compartmentalize that. Entropy is a function of volume. Volume increases, entropy increases. Entropy is also a function of the total energy possessed by the system. And this is going to be a little bit weird to get through, but bear with me. Figure out exactly how to use this example. When you add energy to a system, that energy has to go somewhere. And so it gets distributed amongst the various energy storage mechanisms that you have in your molecules. Remember, our molecules can vibrate, they can rotate, they can have electronic excitations, they can have translational motion. Either way, you stick energy into a system, and it's going to have to be stored in one of those ways, right? And just to start wrapping our minds around it, we'll get into this more on Thursday. But for now, imagine that you've got a system that has 3 energy levels, right? Let's say E1 is some excited state, and that state is 1 joule. So every particle that's in E1 has 1 joule of energy associated with it. E2 is 2 joules, E3 is 3 joules. Let's say that we have 10 particles. We're going to label those 10 particles A, B, C, D, E, F, G, H, I, J, right? And we've got 10 joules of energy. So we've got 10 particles, 10 joules of energy. We've got to distribute that energy amongst the particles. One mechanism that we could do is we could take A, B, and C and stick them in level 3. Now that they possess 9 joules of energy, we've got 1 joule of energy left over. We stick D in there, right? So we stick D in there. All of our energy is consumed. Similarly, we could say that that's not A, B, and C. We could say that's H, I, and J. We could stick H, I, and J in level 3. And then we could stick G in level 1. We consumed our energy. Each of these arrangements, by putting a different molecule in the place that we have one of these guys, it is a different state, a different way to arrange that energy. Even though the same energy levels are populated, if molecule A is in A3 in one arrangement and it's not in the other, then the two arrangements are different. So that's two different ways to arrange the system. We don't have to arrange it this way. We could put molecule A and molecule B in level 3 and C and D in level 2 and then leave all of the other guys in the ground state. But like we said, you can interchange any of these letters. It doesn't have to be molecule A or B or C or D. You can put E, F, G, and H, and I in those states. Let them have that energy. Every single different arrangement corresponds to a different way to arrange that energy in the system. So, I didn't have time to draw all this out perfectly. I'll try to get that done by Thursday. But this is just to wrap our minds around it. Let's say we doubled it. We had our 10 joules of energy, now we've got 20 joules of energy. If we've got 20 joules of energy, we're going to have to put more particles into the higher states. One mechanism for arranging this is to put A, B, C, D, E, and F all up in level 3, and put G in level 2, and H, I, and J can stay in the ground state. Or there's, you can populate all of the molecules in the level 2 to consume your 20 joules of energy. There's a bunch of different arrangements, but I'm hoping that you can imagine that as we go from the place where we're trying to store 10 joules of energy to the place where we're trying to store 20 joules of energy, there becomes a larger number of different ways that we can arrange the system and still have our 20 joules of energy. There's more ways to arrange the system holding 20 joules of energy than there are ways to arrange the system holding 10 joules of energy. And so as the energy content of the system increases, the entropy increases, the amount of disorder. This isn't it's not the best explanation. I'll try to do better on Thursday. I just want to prime you a little bit for problem solving. You did some heating problems. When you're looking at a problem where heat is added to a system moving from one state to another, you're going to start looking for your heat capacities. You know that dQ for a constant volume process is CV dt. dQ for a constant pressure process is Cp dt. And so if we're integrating dQ reversible over T for a heating process, and we're simply going to substitute the dQ reversible for either Cv dt if it's a constant volume process, or Cp dt if it's a constant pressure process, and we'll integrate that, and our equation for the change in entropy will look something like that. C natural log of T final over T initial. Yeah? So we've got volume changes that result in an increase in entropy. We've got temperature changes or energy changes that result in an increase in entropy. Phase changes, there's still heat being exchanged between system and surroundings in a phase change, but to quantify that heat, we can't use the heat capacity. Heat capacity is something that we use when temperature is actually changing. We know that temperature doesn't change during a phase change because all the energy that goes in the system goes into separating the molecules from their intermolecular forces. So they don't actually gain kinetic energy, but they do gain potential energy. And so to communicate the heat that is associated with a phase change, we know that Q is equal to delta H of the process. So if the process is occurring at constant pressure, the Q of constant pressure is equal to delta H. Remember how when we first started looking at the enthalpy, we said that the reason that it was interesting is because it told us what Q was for a constant pressure process. So now if we have one of these phase change processes, and we want to calculate delta S for the process, for those, all we have to do is divide the delta H of the process by the temperature at which the process occurs. So for fusion, delta S of fusion is simply delta H of fusion over the temperature of fusion. Right? And for vaporization, similarly, delta S of vaporization is just delta H of vaporization divided by the temperature at which the vaporization occurs. We'll mention right now, there's a rule that is spoken of in your text. I really hope you guys are reading the text. That's good stuff. It's called Troutner's rule. And it says that delta H of vaporization divided by T, so the delta S of vaporization, for every substance is approximately 85 joules over Kelvin. And that was a little weird. In fact, when I was reading it the first time, it kind of shocked me. But if you think about it, it makes sense. Entropy, a change in entropy, is mostly, if you think about the entropy that's the change in entropy that happens when you have a phase change from liquid to gas, there isn't a lot of additional internal energy dumped into the system because, like we said, all the energy that we use is going to increasing the potential energy. And so the molecules aren't necessarily speeding up. But what they are doing is they're increasing the volume that they occupy, right? And since most substances behave like an ideal gas in that they occupy a predictable amount of volume when they move from liquid to solid or liquid to gas, you would imagine that the increase in the disorder for that process is relatively constant from one species to the other, right? The entropy change is a function of the volume change, and the volume change for all ideal gases going from liquid to gas is approximately identical. And so, in that light, it doesn't seem so shocking that delta S for all vaporization processes is approximately the same. It's not always the same. Water is an exception, as it usually is, because of the very, very, very strong bonding between water molecules. There's actually a larger delta S associated with moving into the gas phase for water than there is for other substances. Okay. I didn't have a chance to scribble out notes because the clock was ticking on chemical reactions, but any kind of a chemical reaction, in general, if you go from fewer numbers of particles to larger numbers of particles, this isn't always true because there's sometimes energy or larger macromolecules have entropy associated with their motion of their bonds, but given two particles that are the same size, if you go from, or given particles that are the same size, if you go from reactants to products that have fewer number of moles of stuff in general, then there'll be more order. But if you go to larger numbers of moles, there'll be more disorder. That's not always true. You have to look at every case individually. What is true about chemical reactions is that, in general, any chemical reaction that results in an increase in the number of gas phase species is going to have an increase in entropy. So if you're producing gas, all of a sudden you're occupying a much larger volume than you were before, and so the amount of disorder increases greatly with an increase in the number of gas phase species. If you see a reaction where gas is consumed and you have fewer moles of gas in the products than you had in the reactants, then in that case, the order of the system is increasing, and so entropy is decreasing. So what I want to do now is just look at your homework and put you guys together in a group and do a few, do about an hour of problem solving. We'll start you off with your homework problems and try to get, don't try to solve all of the problems exactly right now, but set them up and make sure that everybody understands the setup. And Once you've got the problem set up and you feel like you know how to go about solving it, then put that problem down and move on to the next problem. Because we want to burn through as many of these problems conceptually as we can. So let me see if I can find one here.
I would have just like, yeah, sure. It's gonna be like some.
The last one? It was a good night.
Not that
glass. Because you can see your whole systems or not. Maybe it was a
No, there's only one outlet.
It's the worst.
That's really bad.
I have like different pathways and I know you're saying, but
Hey, so that thing, first.
Yeah. Oh, they sent me an email today. So I need to be more specific on actually what I'm doing. And then when I'm doing that, I can email them back and ask them if they're going to change.
besides the separate
Because I have all the
values.
signs bad and you guys see them. So
Yeah, right? It should be more negative, right? Yeah,
Because this is just kind of confirming this.
Yeah,
Yeah.
right? Right?
Yeah. How do you explain it though? Yeah, I don't know. I took a class and then.
It has the answer for like in the whole
I hate the class. The class is so bad.
Okay, so this is homework number 1. Or sorry, number 1, number 3, this is the homework that was recently posted. Did any of you guys download this? Do you have any of you have it on your machines?
Oh, yeah, we can.
Okay, form groups, start looking at these problems. If you need to scroll down, just come over and scroll down to the computer and look at the problem that you need to look at. And start talking about these. I'm going to step out and use the boys' room, I'll be right back.
Homework with advice. Should we do homework without advice first?
No, I opened up that file and it's not the right file. This is the right file.
Oh, okay. So we have to have homework with advice file?
Yeah, is that the one that's on iRead?
Well, there's 2 on iPad right now.
So for.
Do the one that matches this set.
Okay. That's really important, Jim, because I'm at 14%
What I kind of like to do, we've got a full hour. Once you get the problems figured out, you know how to solve them. Anyone who wants to volunteer to stand up on the board to describe how to solve a problem, that would be awesome.
Let's
get started.
A refrigerator made from no engine operated.
This is bar. This is bar for. Bar for.
I think that's the old one.
So this is.
Oh, yeah, okay, so just homework 3.
The refrigerator is the main function of the nut.
Okay. So we have to look at the equations.
What is the
Cardinal equation.
It's that weird graph.
Yeah.
Yeah,
I had the 2 and then I had when it started the Wi-Fi was starting to glitch. I was like,
I dropped this multiple times already.
I know, but then and everything else worked fine. It's just the stupid thing was like my Wi-Fi will only work when I'm at home.
So it doesn't connect when you're out.
But when I'm outside, like it won't connect to anybody's. Like I went to Starbucks, like anywhere.
That's weird. That means your Wi-Fi was glitched out, yeah.
Right, so
Okay, so that's
if
just.
I don't have
But
any
that's
Wi-Fi,
pretty easy.
at that time, I got this one.
That's
The
it.
onset. Oh, yeah. I wanted to ask you.
What
No, I noticed I saw you.
No, it just gives you a coefficient.
Thank you. Not that old.
But how would you derive, okay, so we know that's the answer. How do we derive?
That's what I have from my physics notes.
Seven?
Wait, so coefficient is.
I'm 28 now.
Are you serious?
There's no two?
No.
No way.
Oh my, from my physics.
She's older than me.
Isn't it a coefficient?
No, me and him, we always mess with each other's age back when we had quant lab together. Remember, I was the one who was sensitive the most. I was probably older than all of us.
No, Sarah.
No, wait, doesn't actually tell you.
Oh, so
Yeah, it's still, there's no hint.
So we're gonna have you plan out the lens in 2
Yeah.
years?
Sarah planning on right now, but I told her I'm ready to write
Are
I need
you
to focus
serious?
on church.
In school, are you graduating?
Did you wait? So what was the?
I'm supposed to end this semester, but
Oh,
then.
this is
So you have to do PM2 next semester.
Me neither.
And biology. So after that, I'll see you next month.
Does anybody have that equation?
Is it on his almost still here with us? Isn't that Entropy
Which one you want?
capacity notes or or Entropy notes? She has the evil version of it.
Okay, you look at the equation.
I should have took the evil version from you.
Yeah, the efficiency then is defined by definition of QH.
To yourself now.
Oh, no, because like, I don't know how to put it in there, and then, I just know it. You know, like the icon. Like, you're plugging in your computer, this one, and then.
Oh, you check it
for
into
the
the
iTunes.
So
iTunes, you just,
the
you know, the
coefficient
automatic.
the efficiency
Yeah.
n.
Oh, yeah, that's not even.
Yeah, later on I find
Like
out.
icons, it doesn't go.
Right, so that's
Yeah.
n is the efficiency.
So you don't need to download it, you just
No,
copy
I
and
mean,
paste it.
no, for example, literally like iTunes, you have to have iTunes operate in your Apple devices.
Oh, we do.
You can't just drag it from home, like device, like, you know, stuff in there. Did you find that?
So then instead of going this way,
Instead of
it would
pH.
go to the adiabatic first.
Yeah.
And
This
this.
Yeah, so it'll be TC minus TH over TC. Right, because you're trying to cool it.
Okay, so for work, what is work in adiabatic?
Yeah, is that the book?
Yeah.
Yes. Work is what? Oh, but that has nothing to do with it.
I'm tired too. That's not just at work. You work?
Where do you work?
So if you're with the staff member, probably going to do this personal file, because I know it's followers, team members of the insurance.
Oh, you don't have to go anywhere. It's just go on campus.
Or change in.
Do you get campus parking? Like,
I don't drive there.
Oh.
No, because I took things that were from human resources where we have the faculty and staff
Right, because.
folders in there.
Oh, no.
You're at home?
No, it wouldn't be.
We were organizing the folders and I was like, oh my god, I got this. But because I have all those information.